Greetings and welcome to lecture number 7 on unit number 3, that is fluid kinematics. This lecture we are going to discuss some more functions in fluid kinematics, that is vorticity, stream function, velocity, potential, and the concept of flow net. Actually, these functions are also used for describing the flow field. The main use of these functions in the coding of computational fluid dynamics. So where these functions reduces the variables, and the coding length can be substantially reduced if we use these functions instead of other velocity components. As far as the undergraduates syllabus is concerned, you have to understand these concepts, their definitions, the expressions, and the expressions can be used for solving numericals related with this concept. The first, that is angular velocity, the first terminology or first term, that is angular velocity. Angular velocity generally exists if there is a rotation of the fluid particles. So in case of rotational flow, this angular velocity exists. We already discussed the rotational flow. The flow near the boundary is always regarded as a rotational flow. So there, the normal velocity gradient exists. So as per the definition of angular velocity, it is the average angular velocity of two perpendicular line segments of fluid particle. A flow may be thought of as a motion of collection of fluid particles. As the particle travels along, it may rotate or deform. The region of the flow in which the fluid particles do not rotate are referred to as a irrotational flow. So this is actually happen in case of rotational flow, means flow near the boundary. There is a relative motion between the solid surface and fluid. And because of this relative motion, there is a possibility of deformation of fluid particles near the boundary, as well as the rotation of the particle. So in order to calculate this rotation, we consider a small fluid element that occupies infinitesimal volume, that has xy phase as shown in figure. So this is as it is shown on xy plane, means this is for we are considering as a 2D flow. The angular velocity about z axis, so we consider the rotation of this particular element along z axis is the average of angular velocity of two perpendicular line segments as per the definition. So here we consider the line segment AB and line segment CD, and consider the counterclockwise being a positive. Now the rotation of this line segment happens because of the variation of the velocity across this particular line. And so, for example, in order to rotate this line segment AB in clockwise or anti-clockwise directions, there must be a velocity difference between these 2 points. So if the velocity is same at A and B, the rotation will not take place. Similarly, in order to rotate the line segment CD, there must be a velocity distribution, that is x component velocity distribution, normal velocity component. So for this vertical component, the normal velocity component is u. For horizontal line segment, the normal velocity component is v. Now, in order to calculate, in order to write the expressions of the velocities at different locations, now first of all, we consider the velocity at the center. So at the center, the x component velocity is u and y component velocity is v. Now we consider the variation of y component velocity along this particular line. Now, from the center, if we move towards right, the velocity increases, that we assume. And if we move towards left, the velocity decreases. This is as per the sign conventions. Generally, the positive direction we consider towards right, negative direction we consider towards left. So same concept is used here. Similarly, the u component velocity is u here. It increases in this direction. So that is upward direction we consider as the velocity component increases. And in the downward direction, this u component velocity decreases. Now this increase and decrease values we can obtain by using Taylor's expression. that we already done the Taylor's expression we have applied in hydrostatic law. So similar Taylor's expression we can use here, which state that f of x plus h, that is equal to f of x plus f dash of x into h. So the same expression we use here. In this case, f of x is v. So the velocity at the center is v. So velocity at b, we can consider that is incremental change, and that incremental change is positive. That is f of x plus f dash of x is dabba v by dabba x. Its differentiation with respect to x, that is because its variation we are considering along x direction. So that's why its variation dabba v by dabba x. And into distance between these 2 points is dx by 2. So this is the expression of v at point B. Similarly, at point A, the expression is same, only in this direction there is a decreasing value. So the same amount which here it increases, the same amount we can deduct from V when it moves from center to A. So this is the variation of V component velocity or Y component velocity along AB. In the same way, we can calculate x component velocity variation along this particular line. So here, if it is u, so as per the Taylor's expression, in this direction, there is a positive change. So u, that is f of x plus f dash of x. In this case, it is f of y, because u is a function of y only. So f of y is u, f dash of y, that is dabba u by dabba y into dy by 2. That is exactly half of this. And the opposite thing here, that is it decreases with same amount, only instead of plus sign, minus sign is used. So this way, we have estimated the velocities at each end of the line segment, that is at B, at C, and at D. Now we will calculate the angular velocity of line segment. First of all, we'll calculate the angular velocity of line segment AB. So as per the definition of angular velocity, it is nothing but velocity divided by arm distance or radius. Because as per the definition of velocity in terms of angular velocity, v is equal to r omega. So r in this case is dx, and the net velocity of line segment AB. So this is omega AB. So net velocity is velocity at B minus velocity at A. So the difference, that is VB minus VA. Now, instead of VB, we can put this expression. Instead of VA, we can put this expression. This expression we can put here. So divided by dx. If we simplify this, omega AB, that is equal to, only remains that is dabba V by dabba x. Okay, so here it is dx by 2 into dx by 2 is dx 2 dx by 2. So 2 get cancelled. So dx get cancelled. That's only remaining is dabba V by dabba x. As this rotation, we can say as the B velocity is greater than A velocity, this particular line segment rotates in counterclockwise directions or anti-clockwise directions. That's why the positive sign is used. Similarly, the angular velocity of line segment CD we can define, and it's as per the definition, the angular velocity of line segment CD, that is equal to the net velocity of line segment CD, that is VD minus velocity at D minus velocity at C divided by dy. Now, instead of velocity of D, we can put this expression, that is u plus dabba u by dabba y into dy, minus we can put this, that is minus into bracket u minus dabba u by dabba y into dy by 2 divided by dy. Now, in this case, the negative sign is used because if we see the rotation, obviously the velocity at D is greater than velocity at C. So this particular line segment rotates in clockwise direction because this point moves at a faster rate than this point. So obviously this particular line segment, it rotates in clockwise direction, and clockwise direction we consider as a negative sign. So negative sign is introduced. After simplification, we get the value of omega CD, that is equal to minus dabba u by dabba y. So these are the values of two perpendicular line segments as per the definition of angular velocity. angular velocity about z axis, that is omega z, that is equal to average of angular velocity of two perpendicular line segments. So in this case, that is omega AB plus omega CT divided by 2. After substituting the values, we get omega z, that is equal to 1 half into bracket dabba v by dabba x minus dabba u by dabba y. Now this is angular velocity about z-axis. Similarly, we can obtain the angular velocity about other two axes, that is x and y. So for that, we can use some thumb rule here. Now, if we see this particular expression, the angular velocity about z-axis, if we have to determine, first its variation with respect to after z, it comes x, then comes y. So while writing the expression, you can omega z, that is equal to 1 half in bracket. First of all, we'll write differential, that is dabba x, minus second, we can write the differential dabba y. And then we can put the y component velocity in opposite term. So here the y direction. So y velocity component we can put here. X velocity component we can put here. So that completes the expression. So this way we can develop the expression of omega x, omega y. So I repeat once again, that is omega z, that is equal to 1 half. So if we see as per the sequence, after z it comes x, after x it comes y, and these are the normal velocity components, means the same direction velocity is not there, opposite direction velocity is there. So obviously y component velocity we can put here, x component velocity we can put here. Now you can check the omega y. Omega y, we can, if you have to derive the expression of omega y similarly. So after y, it comes z. So we put first dabba z here. Then after z, it comes x. We put dabba x here. So x component velocity, we can put here, that is u. Z component velocity, we can put here, that is w. So remaining expressions are same, 1 half other things. So this way we can estimate the normal velocity component. All these are the normal velocity gradient. Okay, so this is not the velocity gradient along the same axis, it is along the perpendicular axis. So the same velocity component we can put in reverse manner. Similarly, now omega x, after x, then y, and then z. So after x, we can write here dabba y first, then dabba z, then z component velocity we can put here, that is w. Y component velocity we can put here, that is phi. So this way, we can obtain the expressions of other angular velocity or other direction angular velocity, that is omega x, omega y, and omega z. So this is about the angular velocity. And in case of rotational flow, this angular velocity exists. Now, vorticity, as per the definition of vorticity, it is a circulation per unit area, but it is common to define vorticity. It is generally denoted by capital omega. Small omega that we use for angular velocities. Capital omega is used for the vorticity, and it can be defined as a twice of angular velocity. So as per the previous expression, it is a twice of angular velocity. So if you multiply 2 by expression of angular velocity, it becomes like this, omega x, that is equal to this omega y. Only half uh, term is eliminated from the previous expression. It becomes the expression of vorticity. Or an irrotational flow possesses no vorticity. So vorticity vector we can define in this way also, that is omega bar, that is equal to omega x I hat plus omega y j hat plus omega z k hat. And if you substitute these values of omega x, y, and z, it becomes like this. In matrix form, we can write in this particular form. And from this matrix form, we can see in generalized vector form, we can write omega bar, that is equal to curl of velocity vector. So this is a curl of velocity vector because it's cross multiplication. So for example, for omega x, we can take the cross multiplication of this, that is dabba w by dabba y minus dabba v by dabba z. So cross multiplication in vector, that is called as a curl. So this is curl of velocity vector. So that is omega bar. So this is a generalized form of vorticity vector, and especially this vorticity vector is zero for irrotational flow. So this is about vorticity. So uh, then some functions are used, and these functions are especially used for convenience. So instead of, if we have to uh, describe any flow field, instead of describing all the velocity components and other relevant things, so only by describing some functions, it has some characteristics, so we can reduce the number of variables. Now, velocity potential, how this term is introduced, that we'll see. So we have, according to the expression of vorticity, that is omega bar, that is equal to curl of velocity vector. So for irrotational flow, that it is generally zero. So if we consider V bar, that is equal to del phi, del or phi is any scalar quantity, then if we put this V bar in this particular expression in terms of del phi, it is uh, uh, omega bar, that is equal to curl of gradient of any scalar quantity. So as per the definition of vector rule, or according to the vector rule, the curl of gradient of any scalar quantity is always zero. So what it indicates, if we add this particular term in this expression, the vorticity component or vorticity vector becomes zero. That, and for which type of flow vorticity vector is zero, that is for irrotational flow. So for irrotational flow, vorticity component or vorticity vector is zero. And according to the vector rule, when it comes zero, when you make this substitution, so substitution, what that instead of V bar, if we put the gradient of any scalar quantity, so curl of gradient of any scalar quantity is always zero. You can check this. And so this substitution makes the flow irrotational, that is interpretation. Now this phi function, so now if we put the expression, that is V bar, that is equal to U into I hat, this is V bar is a velocity vector. So this is expression of velocity vector. Del phi is also a vector, and this is the expression of del phi, that is del is nothing but dabba by dabba x into I hat, like that, and phi term is there. So dabba phi by dabba x into I hat plus dabba phi by dabba y into j hat plus dabba phi by dabba z into k hat. So if with this, if you split this, instead of V bar expression, that is velocity vector, we write here, then del phi expression we write here. Now if we compare this, U is equal to dabba phi by dabba x, V is equal to dabba phi by dabba y, and W is equal to dabba phi by dabba z. Now in this case, this phi is called as velocity potential. Why it is called as velocity potential? Because if the phi, if you substitute in the vorticity vector in gradient form, it makes the flow irrotational. And steady irrotational flow is also called as a potential. So that's why this term, phi term, is called as a velocity potential. So this is a substitution, and this substitution is made for introducing this particular term. So because of this substitution, the flow becomes irrotational. And this substitution term, that is phi, is called as a velocity potential. This velocity potential phi, it can be defined as a scalar function of space and time, such that it's so if we define the this particular term, so we can define in this way such that it is a scalar function of space and time, such that its partial derivative with respect to any direction gives the component of velocity with respect to that direction. Suppose if we compare these two, and from compare after comparison, we can say that is u is equal to dabba phi by dabba x, v is equal to dabba phi by dabba y, and w is equal to dabba phi by dabba z. So from this expression, we can define this function. So it is a scalar function of space and time such that its partial derivative with respect to any direction gives the component of velocity in the same direction. So if we differentiate this function with respect to x, it gives x component velocity. If we differentiate this function with respect to y, it gives y component velocity. And if we differentiate this component with respect to z, it gives z component velocity. So this is the expression of u, v, and w. And now, according to continuity equation, if we put this particular expressions, that is expression of u, v, w in terms of phi, this is a continuity equation. So in three-dimensional flow. So instead of u, v, w, if we put this expression, it becomes dabba 2 phi by dabba x square plus dabba 2 phi by dabba y square plus dabba 2 phi by dabba z square, that is equal to 0. So here we can, the square term is missing actually. But this particular expression where phi is called as a Laplace equation. So this expression is called as Laplace equation. And so in we can say that so phi function must satisfy Laplace equation for continuity of flow. So this is another characteristic of phi function, that is if it exists, then we already say that if it exists, the flow is potential. But in order to satisfy whether it satisfy the Laplace equation or not, or if this phi function satisfy the Laplace equation, then the flow is possible. If the flow is possible, then obviously the flow is irrotational. So that is, again, we can prove that if we substitute this, we have omega z, suppose for 2D flow, we consider omega z, that is equal to dabba v by dabba x minus dabba u by dabba y. And if we substitute the value of v and u in terms of phi, so this is automatically 0. That means if this function exists, the flow is potential or the flow is irrotational. So these are the two major characteristics of velocity potential. If the velocity potential exists, the flow is irrotational. And if it satisfies the Laplace equation, then the flow is possible. And if it doesn't satisfy the Laplace equation, in that case, it is incorrect form of velocity potential. So uh, uh, in order to make the flow possible, then the question arises that it is irrotational. If the flow is possible in case of velocity potential, then the flow is always rotational. But if it doesn't satisfy the Laplace equation, then the flow is not possible. Then there is, if the flow is not possible, then there is no question arises whether it is rotational or irrotational. So in that case, that velocity potential, it may be incorrect. So these are the characteristics. So what is the importance of this velocity potential? Means only if this potential, it is an indicator of irrotational flow. If this potential is available in correct form, it is nothing but indication or indicator of a. So instead of proving that whether the flow is rotational or irrotational, instead of putting the values of velocity component in the rotational component, that is Vorticity component, then prove that. So that proof is not required. So it reduces the uh, variables. So variable in the sense that angular velocity, vorticity, then velocity component. And so with the existence of this potential function, it is an indicator of the flow is irrotational. So this is the importance of this velocity potential. Second function that we will discuss, that is a stream function. So we know the continuity equation for 2D flow, that is dabba u by dabba x plus dabba v by dabba y, that is equal to 0. And which motivates the definition of u and v. If we let u is equal to dabba psi by dabba y and v is equal to minus dabba psi by dabba x. And if we put these expressions in this continuity equation, we can see that is dabba 2 psi by dabba x dabba y, that is in plus sign. And here dabba 2 psi by dabba x dabba y minus sign. So it gets eliminated. So continuity equation automatically satisfied. So accordingly, we observe that the continuity equation is automatically satisfied. So that's why this scalar function means, like in previous where that velocity potential exists, the flow is irrotational. Now here, if you make the substitution of u and v in this particular form, that is in differential form of psi function, then the continuity equation is automatically satisfied. So that's why again from this particular expressions we can define now the this scalar function, that is stream function or psi function. So this scalar function, that is psi, is called a stream function, which may be defined as the scalar function of space and time such that its partial derivative with respect to any direction gives the component of velocity right angle to that direction. Because if we differentiate psi with respect to y, it gives the right angle direction velocity, that is u. And if we differentiate psi with respect to x, it gives a right angle velocity component, that is v. So obviously, or we can say, suppose if we differentiate this component along a vertical y direction, so right angle velocity component is u. Or if we differentiate this component along a horizontal direction, that is positive x direction, so its right angle velocity component is minus v. So only minus v, minus sign we have considered here. So from these two expressions, because this is a substitution, and from these two expressions, we can define a stream function in as this is a scalar function of space and time such that its partial derivative with respect to any direction gives the component of velocity right angle to that direction. So dabba psi by dabba y gives x component velocity, and dabba psi by dabba y, x gives y component velocity. Now, why this particular function is called as a stream function? So now we consider this is the equation of streamline. So in this expression of streamline, if we put the values of u and v here, now first of all we rearrange this term. That is for 2D flow. That is u into dabba y minus v into dabba x, that is equal to 0. So instead of u, if we put dabba psi by dabba y, instead of v, we can put minus dabba psi by dabba x. So minus minus get plus. So this is the expression. And according to chain rule, this particular term is called as d psi. So d psi is equal to 0. If we integrate it, psi is equal to constant. Thus, psi is constant along streamline. That means this function remains constant along streamline. That's why it is called as a stream function, because it is a function of streamline. So the stream function name is given after this particular expression, because this function, if you put the values of u and v in terms of stream function, then the psi is equal to constant. That means this function remains constant along streamline. That is one thing. Then secondly, the vorticity vector for a plane flow, generally for plane flow means 2D flow, there is only one component, that is a z component velocity, since w is 0. So omega z, that is vorticity z. Now if we put the values of u and v in terms of psi functions, dabba psi by dabba y and dabba psi by dabba x, then it becomes dabba 2 psi by dabba x square plus dabba 2 psi by dabba y square, that is equal to 0. It is not comes equal to 0, because this is equal to, this is minus dabba 2 psi by dabba x square. This is also minus dabba 2 psi by dabba y square. And when it is 0, when this particular term is equal to 0 for irrotational flow, means This is not automatically comes zero. If this equal to zero, that is a Laplace form, then the flow is irrotational. That means if the psi function satisfy the Laplace equation, then it is a possible case of an irrotational flow. But if the psi function exists, we already proved that this substitution, if it exists, it automatically satisfies the continuity equation. And continuity equation means it is a possible case of flow. Means if the psi function exists, then the flow is possible. And if the psi function satisfy the Laplace equation, then it is a possible case of an irrotational flow. So the stream function has measured these characteristics. So if the stream function exists, the flow is possible. If the stream function satisfy Laplace equation, it is a possible case of an irrotational flow. While velocity potential exists, the flow is irrotational. And if it satisfies the Laplace equation, it is a possible case of an irrotational flow. So in order to prove whether the flow is possible or whether its flow is irrotational or rotational. For irrotational flow, both functions have to satisfy Laplace equation. Means Laplace equation means double derivative of that function with respect to x plus double derivative of that equation with respect to y. It must comes equal to zero. If it comes equal to zero, then it the flow is irrotational. So for uh, proving whether the flow is rotational or irrotational, instead of estimating the vorticity component, if these functions double derivative with respect to any direction, and all three direction if we consider, and addition of all it comes equal to zero, then the flow is irrotational. In case of velocity potential, we have already seen that if it doesn't satisfy Laplace equation, then it is called as the incorrect form of velocity potential. Because if velocity potential, if it doesn't satisfy the Laplace equation, then the flow is not possible. And if the flow is not possible, then there is no question arises whether it is rotational or irrotational. That's why that phi function is, we can say it's an incorrect form of potential. So these important characteristics you have to memorize or must understand for solving various numericals. So these are the two important functions generally used to minimize the number of variables. So this number of variables, that's why in most of the vector form expressions, they are used in computational fluid dynamic coding. So the main use of these two functions in the computational coding, and these functions are also used to describe the flow line. Now, as far as the streamline is concerned, stream function is concerned, the flow is possible. This stream function can also be used to determine the flow. Now, if we consider the two stream functions, psi1 and psi2 on xy plane, and this is a streamline. So across this is a velocity potential line, we can say, and across that flow is possible. Now we have to calculate this discharge through this particular streamline. From this streamline, so we consider dq that is equal to dq1 plus dq2. Dq1 is the flow through bp plus dq2 that is flow through ap. So dq1 plus dq2. Now if we consider this is the resultant velocity v. So it has two component. So resultant velocity in this direction, it has downward y component velocity and upward x component, or sorry, towards right, positive x component velocity. Okay, so velocity, because here this is y component velocity, normal velocity component is y, so y component velocity is negative and x component velocity is positive. That is according to the vector rule. Okay, so this is a resultant vector. It comes addition of this plus this. So as per the direction, this is a negative y direction. So that's why we consider this is a negative v. So similarly, here we can put this minus v into dx. That is a flow rate per unit. We consider the width is unity. So the area of this particular passage, that is dx into 1. So v into dx into 1. So here dq1, that is the discharge, that is area into velocity. Velocity is u and the area is dy into 1. Minus minus sign is, that is plus, actually plus, but here it is minus. Velocity component is v into area is dx into 1. Now if we put u is equal to dabba psi by dabba y and v is equal to minus dabba psi by dabba x. So after substitution, we get dq is equal to this. So this term is called as a d psi. So dq is equal to d psi, or integrating we get q is equal to psi 2 minus psi 1. That means the discharge between streamline is given by the difference of two psi functions, psi 2 minus psi 1. So this psi function can also be used to calculate the discharge or to determine the discharge between two streamlines. So especially these functions uh, are used for calculating discharge virtually in the CFD analysis. So this is dq is equal to psi 2 minus psi. Now the flow net concept, especially if we use this two lines, that is equipotential lines and this constant stream function line, then it becomes a flow net. Now, first of all, we derive the expression of equipotential line. Equipotential means potential function, the line along which the velocity potential phi is constant is called as equipotential line. For equipotential line, phi is equal to constant. Therefore, d phi is equal to 0. If phi is the function of xy for steady flow, then according to chain rule, d phi is equal to dabba phi by dabba x into dx plus dabba phi by dabba y into dy. So instead of dabba phi by dabba x, we can put the expression of that we can put u, or instead of dabba phi by dabba y, we can put v. So the expression is d phi is equal to u into dx plus v into dy. For equipotential line, d phi is equal to 0. So equating this to 0, we get a slope for equipotential line, that is dy by dx is equal to minus u by v. So we call this equation number 1. Similarly, same exercise we do for constant stream function line, or this is called as equation of, or along streamline. That is called as a streamline. So because along streamline, stream function is constant. So it is a line along which the stream function is constant. So this particular line is called as, sorry, this is a printing mistake. It is not called as equipotential line. It is called as a streamline. So along streamline, psi is equal to constants. Therefore, d psi is equal to 0. But psi is a function of xy for steady flow. So d psi is equal to dabba psi by dabba x into dx, dabba psi by dabba y into dy. If we let u is equal to dabba psi by dabba y, and v is equal to minus dabba psi by dabba x, and if you substitute there, so d psi is equal to minus v, because instead of dabba psi by dabba x, we can put minus v. Instead of dabba psi by dabba y, we can put u. So for streamline, dabba psi is equal to 0. So by putting the value of, so minus v into dx plus u into dy, that is equal to 0. So slope for streamline, that is dy is equal to v by u. Call this equation number 2. Now, equation 1 and 2, it is clear that the product of slope of equipotential line and slope of streamline at that point of intersection, that is equal to 1 or minus 1 if you take a product. Thus, the equipotential line and the are orthogonal to the streamline at all points of interaction. So this we can. So sometimes the proof can be asked. So prove that equipotential line and constant stream function line are orthogonal to each other, or their product of slope is equal to minus 1. So this proof can be asked. So now if we draw these lines, that is a constant stream function lines, if we draw in this direction, exactly the 5 lines we can draw orthogonal to these lines, that is perpendicular to these lines. So this particular grid is called as a flow net. So it is a grid obtained by drawing a series of streamlines and equipotential lines. The flow net generally provides a simple graphical technique for studying two-dimensional irrotational flows, especially in cases where mathematical relations for stream functions and velocity functions are either not available or rather uh, difficult and cumbersome to solve. So under that circumstances, the flow net is used. So the flow net generally used for calculating the leakages as well. Suppose this is a dam structure. Maybe it is made of soil, and if there are some porosities present, then exactly this is from high level to low level. So obviously the pressure here is greater than the pressure here. So where the leakages comes from, that we can easily recognize with this particular technique. Ladies. So this is actually this one experiment where this is at the high level, this is at the low level, and if the color dye is introduced here in the soil, you can see it takes the form of streamlines. So these are the different streamlines because here the level is low, here the low level is high. So obviously the flow taking place from this side to this side. So it forms streamlines, and perpendicular to this is the equipotential line. So same technique is used, flow net technique is used to recognize this time. So suppose this is a flow line, and these lines are perpendicular to this, that is equipotential lines. Then it is called as, so the uses of flow net. So uh, the main uses of flow net, that is determination of design of outlets for their streamlining. So outlet we can define using this particular technique. It may be used for the quantity of seepage and upward lift pressure below the hydraulic structures, especially soil structure where the seepages quantity can be determined. It can be used for determination of streamlines and potential lines. It is also used for determination of pressure and velocity distribution for given boundaries of the flow. There are certain limitations of this flow net as well. The flow net analysis cannot be applied in the region close to the boundary where the effect of viscosity are predominant. So because generally the streamline, the viscosity is considered as negligible, but the viscosity effects are dominant, then in that case, this flow net analysis fails. And in case of flow of fluid past a solid boundary, while the flow net gives a fairly accurate picture of the flow pattern for upstream part of the solid boundary, it can give a little information concerning the flow conditions at the near because of separation and ADs. So especially in some cases where the flow is affected by viscosity, there it gives a little error. So it is generally applicable for potential flow, that is irrotational flow. For irrotational flow only, this particular concept is more valid. So that's it from this particular lecture. At this end of this particular session, you should be able to describe these various terms, that is angular velocity, its expression, then vorticity, stream function, and velocity potential function. Especially stream function and velocity potential functions, they have certain characteristics, and they have characteristics exactly opposite to each other. So you have to memorize these characteristics and the expressions for solving numerical. So you should be able to describe the concept of flow net as well. So what is flow net? What are its uses? What are the limitations of the flow net? All this concept you must know. You should be able to describe. So that's it from this particular session. Thank you very much.